let's start. And I guess a good point to start will be an introduction. Could you please describe what you were doing in your career, where you are right now? So just to get the gist of this, we're going to talk today. Yeah.
All right. So, hi everybody. I'm Wojtek Burkot. As you can see, I'm old. So the Sergey asked about talking about my career is kind of funny because it's a long story. So I started as a physicist. I did my part in designing and building Hera accelerator and then Zeus experiment there, and then running this, getting physics out of the machine. Getting physics out of a machine is kind of useful in the quantum computing as well, but that was a long time ago. Then I moved to the dark side of business. So I spent 8 years managing at Motorola and for Motorola, which I hated most of the time. So I ended up my career at Motorola as an individual contributor, building one of the first nationwide Tetra systems for Hong Kong at that time. Then it was Google, 8 years, engineering director, hired to set up Google engineering site in Poland. I chosen Krakow as my hometown. It was a good time, young Google and bright people, good stuff. Then a short stint at Allegro, the huge e-commerce site in Poland, which was a mistake. As people say, first job after Google is a mistake, right? So yeah, it was a mistake. And then I decided to start with a long-time friends of mine to start Beit, based on the idea which I had many, many years back when I was still with in academia. Got invited to MIT, met Professor Tommaso Toffoli, Toffoli Gate, and met Professor Norman Margolis, the Margolis Gate, working at MIT on something completely different, but still the other physics paradigm for some different computations. It was cellular automation built in hardware, not just the simulated one. So, and then I got the quantum computing bug. I thought I understand how it should operate, and based on that idea, just 30 years down the road, we created, no, it was 25, sorry, not 30. We created Beit and started turning those ideas into reality. And that's more or less today. So happy to talk more about what we are doing.
Yeah, just looking at what you just said, I definitely want to ask you a lot of questions, but I think let's maybe go to the most recent step. It's quantum technology, and Beit is a quantum startup, because when I looked at the most promising quantum startups, the number of 100, and the Beit was in this list. So is it like a quantum startup, or how you position it, Beit?
Well, we are a startup, most definitely. We don't make revenue, and if somebody does, I think they are not completely honest with their customers, because, take it from me, the quantum computers of today are no match for high performance computing done in huge data centers. I've been on both sides of this, and I know that for the fact. So currently, there is no business problem which you can solve on quantum computer more efficiently than on the classical one. You can take my word for this, and if you don't, then I dare you to bring the problem our way. So if you have a problem which somebody says they are solving on quantum computer, and it is business relevant problem, we can solve that easier and cheaper using classical techniques in the same Beit team. And we do some sort of the quantum inspired thing, so different paradigm, like the annealers, classical annealers, like Fujitsu, for example, patterned after D-Wave. And yeah, this is different and just massively parallel and does stuff. However, Beit aims for the future, in a sense that, yes, there are reasons to believe that quantum computers will eventually be stronger than the strongest classical one. We can talk for hours about what are the signals, but it is not today. And we know that there will be a quantum winter. Again, if you want to check, Go see the Gartner predictions on the hype curve where the quantum computing is for the last 4 years, right? Not that they have any clue, right? They know how to sense the sentiment of investors and potential customers. I don't believe that they understand much about the difficulties of quantum computing, but essentially quantum computing on their most recent graph is still 10 years away and nearing the peak of their hype curve. So really bad moment and you can see this, right? You said 100 startups. When we started, there were like 80 people globally doing software for quantum computing. I know that there's many more now. Some of them we work with because I think we're taking overlapping yet different positions in the software stack of quantum computers. But yes, there's many more, and some of them actually do real interesting stuff in quantum computing.
But so what you're saying that right now we're sort of pumping the bubble of quantum computer with buzzwords, because what you said is, I think it's very important that right now there is no real problem where the quantum computer is really better than the classical computer.
Well, I need to put a caveat to this, right? Everybody heard about Google supremacy experiment. It was real. It was beautifully designed, physical experiment on the hardware. However, it essentially emulated Sycamore on the Sycamore. Right? Well, while they claimed they would emulate Bristlecone on Bristlecone, Bristlecone was bigger, never materialized in the public, right? It's hard. It is just hard. And there are two other cases where something probably computationally hard, classically, has been done in real matter. This was Chinese experiment on boson sampling, taking the distribution, which had correlations because of the quantum phenomena that they had in the interactions. And they showed that it's hard to actually predict that distribution classically. And most recent result, the Polish guy, Michał Oszmaniec from Warsaw, slightly modified fermion sampling and got similar results, something which is computationally hard for the classical computer, and yet can be shown to work on the experimental setup of the quantum computer. But those are specific. Those are not universal computations. They are not business relevant in any way, right? So that's my real claim. Business relevant problem being solved on the existing quantum hardware.
But so
no such a thing.
Yeah, but do you think it just for now, because the quantum
otherwise we wouldn't be working in Beit, right? We do believe that it would come sooner or later, and we want to be among the survivors of the deep of the throw of the disillusionment of the Gartner hype curve, right? We want to emerge on the other side, doing real stuff, and that's how we started. We patent a lot. We publish a lot of the unique results, and we were able to show it on the real quantum hardware stuff, which is in a way better than the classical one if you count the number of oracles in completely unstructured search. We have proven that we can experimentally demonstrate that we can do that better than classically possible on the actual quantum computing hardware, both IBM and Honeywell.
Okay, but so what you're saying right now, that at some point the quantum computer will get the supremacy, but I think maybe we should give it a bit of more time, because the Google just shows this supremacy thing only like maybe a year ago. So now it's a question of time.
I guess it was 2 years.
Okay, maybe 2 years. Yeah,
you're right.
So, but my point is, like, maybe we should give it a bit more time, because developing such a complicated thing as a quantum computer, and we give it only 2 years, and now it's a question of time when it will be really useful for solving a real deal, right?
That's about $30 billion question, not $1 million question. It's $30 billion question. When you want to invest, when investing is too early because the company is getting your money will fail, because there's too early. It's a $30 billion question. No idea, absolutely. But we decided we cannot tell, predict. So we focused on building the IP, which will be relevant whenever it comes. We might run out of time in protecting it, though. But this is valid. Our patents will hold, and they provide methods which are provably more efficient than what was thought possible. So that's how we try to overcome that part of the uncertainty of the not Heisenberg's uncertainty. It's just the uncertainty in the time where the quantum computers will be around.
Actually, I was thinking that I've heard this idea that maybe the community of quantum computers should be more open in the sense that it will be a sharing idea, sort of like a Bitcoin community when people sharing freely what they're doing. I'm just saying that maybe it will be good, but I'm not sure if it's really relevant.
I can see this in the software world. Yes, we do collaborate with people, potentially our competitors, and Q2B or QCware from the US, Q-Control from Australia. We work with those guys. Combining, we can do more. And there is some sort of sharing. Most of those people are coming from the academia, so sharing is kind of natural, right? Yeah. But you cannot see that in the hardware. In the hardware world, there is a cutthroat competition. Who actually signs up those huge corporates having huge money first? That's what the game is all about.
But what I feel like, considering the hardware, it will be rather a smooth transition in the sense it's not like it will be one day when it shows that now we get the quantum computer. We will slowly increase the number of qubits. We will slowly increase the control over these qubits. So it shouldn't be like a specific day when you get really a nice control over your qubits or over the quantum computer. So it will smooth transition. That's at least my belief.
I don't believe the smooth transition part for the reason I'll be hand-waving mostly through that discussion now, but there is some more substance in some of the claims I'm making. So smooth transition, you say, you know, if you go with any measure of the efficiency of the quantum computer, you can see nonlinear behavior. So if your computation needs certain number of qubits and certain circuit depths, meaning the length of the program which you can still sustain, then getting the gate fidelities below certain number says that no matter how many qubits you add, you will not be getting what you wanted, right? You cannot error correct adding more qubits if you don't start with the appropriate high fidelity of your qubits and gates. So this is nonlinear, and that's why I don't think that there will be a smooth transition. But on the other hand, I don't believe that we have seen the final universal quantum computing hardware, right? If you go and watch the street, right, we are in the revolution about the cars because of the electric and the alternate fuel cars. But right before this, all the cars look the same, because they're optimized by the same software to the same external conditions, right? And you cannot build a car any better than those typical designs. And we are very far from that in the quantum computing world, right? It's superconducting or the ion trap. It is photonics or Majorana particles and the topological qubits. So many concepts means that we are very early in the game. Like, you know, the cars bug in 1902. You will have 6 wheels, 4 wheels, 3 wheels, steam, electricity, internal combustion, all the possibilities, because nobody knew what would be the best, right? So I think we are exactly in this age with the quantum computers of today. And that's why there are so many competing designs, and I believe that we haven't seen the final one yet. I would put bet on photonic computers for many reasons.
Okay.
But yeah.
Yeah, okay. Personally, for me, closer to heart is neutral atoms, but I feel like they're a bit okay. It's really a game. You can choose your preferences. But what I think right now we're talking that we are really in the early stage of quantum computing. But still, even from the public, we have quite a lot of attention, and people who are not really experts in quantum physics, they start paying attention to how this high tech is developing, right? And
oh yeah.
And it seems like
Gartner hype curve, exactly this, right?
But do you think like who inflaming this sort of buzzwords? Because I don't think it's really scientists and hardware engineers doing that. It's people who don't understand what they're doing. Or
There are some people even in the quantum startup world which are making outrageous claims, and they must know. Or, well, if you go into the pedigree, if you go into the CV of some of the founders, and you see no trace of physics at the right level or mathematics at the right level, most likely the chance that they know what they are talking about is pretty low, right? It is complex. People spend years learning this. So you cannot jump from marketing to being a CTO of the quantum computing. There are such cases. Sorry, it's not even funny, right? So I can see those people making the claims you are asking about, and obviously, if somebody makes such claims, it is a news. So journalists would jump on it, right? It's much less cool than telling that essentially we can do the unstructured search better than classical. By the way, finding one marked element among 64. Come on, it's just the blind person with the matchbox and one burned match is exactly the power of the current quantum computer, and it's cutting edge, right? Nobody can do that any better than us, and this is a real experiment. We did this, right? So that's the limit.
Okay, true. But okay, first, of course, I agree that there is marketing, and marketing sometimes could be dark. That's true. But let's take, let's say, consider people who really want to invest and they think it's really cool ideas, but now they're a bit diluted by this hype. So do you think they should invest, or they should like take a stocks?
Well,
I mean, I know that
they shouldn't invest in if they aim at something like the fast gains, right? It will be extremely hard to return something of value within like 2-3 years. I'm not saying that there will not be big acquisitions in that time. There will be, right? So that kind of value you can build, but not the end product for the end user, not in that time frame. No way.
I see, but okay. So, but if let's say we're considering long-term investment, then quantum computing is still a good chance.
Definitely, it's going to happen, right? Physics tells you that it's going to happen for the very simple reason we cannot efficiently simulate sufficiently complex quantum systems. Full stop. Done.
Yeah.
Meaning everything which is of that nature, think chemistry, will be naturally hard for the HPC. No matter whether you start using AI, machine learning, you name the buzzword, but it still doesn't help. It's NP hard. You add a little bit of complexity, one more particle, and the complexity grows through the roof, right? So that's what will stop HPC from ever catching up with the real quantum systems of interest, while it's easy to prove that the quantum computers can do that efficiently.
Yeah, but so what we're saying right now is that technically for the long-term investment, quantum computing is good. Okay, you might not get your gain in 2-3 years, but let's say if you're aiming for 10 years, it will be good. You have to just choose your company properly.
That's the hard part, right? I might wear my other hat. I'm being pissed off with the VC scene in Poland. With a couple of friends, we set up the deep tech VC, right? So I can tell you what's hard about this. In order, you cannot make.
I'm not sure what's VC. Can you just?
Venture capital firm,
okay,
right? We are investing in early stage deep tech companies, startups. So you said pick it right. You cannot, because the making predictions is hard, especially if they are about the future, right? And if your horizon is 10 years, you cannot make the right prediction. There's just no way. You don't have the information. And by the way, the distribution follows the power law. So it will be in the most popular Pareto case, there will be 80% of returns from 20% of picks. Meaning there's no average, meaning you have no way of selecting the right ones. You just need to spray and spray. So invest in very many and hope that some of them will do tremendous returns, right? Those survivals will make tremendous returns, but there's no way of picking them. And there's not enough of them where there are no strong red flags to apply this spray and pray strategy of investing. So it is hard, right? Picking the good quantum computing company now is hard for the investment. You need a long-term horizon, and you need to be able to actually see whether they are on a path to something useful, right? Which means understanding physics and mathematics they are using, if they are using any. If they are done, just forget them. But if they are using this, you need to understand that to verify whether there is some reason behind this.
So what you're saying, let's say, if you want to invest in photonics, let's say you choose your photonics because that's your favorite. So you have to understand what the company wants to do to really invest because
I would think that the answer is yes to such phrase. There is one more thing though, right? The money on the gold rush in California was made on the shovels, not the gold, right? So if you see the technology which is necessary in developing the quantum computers, low power amplifiers able to run in very cold environments, right? Low power, low noise amplifiers for the signal pickup, measurement techniques, right? Single photon sources. You can name several technologies which are not quantum computing, but will be necessary. And I think if the smart investing should involve something like this, right?
Yeah.
Again, you need to understand this, but then you can go into what's necessary. What do we have? Single photon sources, right? The cables which run from the room temperature at one end to millikelvins at the other end, and still are not noise, not breaking, and so on and so forth, right? So you can select certain technologies which exist already and invest in them, in sufficiently many of those. So whatever the quantum computer is, you will have your bet into something which is necessary for it to operate.
Yeah, and do you think that this is really a place for quantum consultancy? Because now let's say people who want to invest, but they don't know physics, but they want to invest. So they should hire people who know how to quantum.
And then they should hire people who can check on those people who, and so on and so forth. I used to be, I skipped that. I used to be a consultant too. And we are actually developing the billing systems for large telecoms. So I more or less understand how they operate. And I wouldn't trust consultants in telling me whether I should invest my money into the company they picked, right? The chance that they have the necessary skills to assess is pretty low.
But do you think that then maybe you should hire a person who is expert in specific, let's say, computers on photonics, let's say quantum computers on photonics? Maybe this person could give you more information, because you still want to invest, right? Eventually, you have to pick up your information somehow from some source.
Well, I'll go, if I wasn't a physicist, right? I'll go and find the physicist friends and have a long conversations with them, trying to understand. They might be wrong, as I might be wrong with my choices, right? But having sufficiently many will let you build the kind of, not the detailed understanding, but at least the limitations, right? If you ask me now, I can tell you what I see as a problem. And actually, we were telling this from day one when we started building Beit. So for the particular, depending on the technology, right? The IBM announced the big project called Condor for the next year roadmap. Do you know what it is?
No, sorry, no.
It's a big chiller. They are trying to bring much more substance to millikelvins, because without that, you cannot scale the quantum computer. You can cool down 25, maybe 50 qubits, and that's it, because getting energy out of near absolute zero is nearly impossible, right? It's just pure physics, thermodynamics. What is the cooler thing? How you extract energy, right?
Yeah.
So for them, the problem for the superconducting qubits, the chilling at the millikelvin scale is a problem. And then especially as you are getting a lot of thermal energy via any control wires getting from your computer down to those millikelvins, right? So it is hard, and that's why they focused on building just this. And you can go in the similar things for the ion trap machines, which those two types are dominant at the moment.
Yeah. So, but pretty much what we are saying is that there are some platforms they will be developing, and right now we cannot say which platform will be the best. So we have to invest in as many as we can and hope that one of them will really shoot out and produce.
Well, I would try to be slightly more clever, investing in things which make those platforms run. So the cables for the superconducting ones and the chillers, yes, who makes the best ones? And for the photonics, the single photon sources, that's the stuff where you should be investing. Very similar things, plus the technology to do that on the chip for the ion trap machines, in a sense that eventually you need to, do you know how the current
ion traps working?
You know this. So it's huge installation, right?
Yeah, I know.
Lots of lenses, lots of lasers, and you cannot build a computer like this, right? So people are trying to make them on the chip, right? Have a laser, have the ion trap on the single chip or build on silicon. And it's going to happen, obviously, right? The miniaturization. And then connection between them, either electrical or optical via lasers. You need to build this in a modular way. So again, the technologies which make that happen, that's the place to invest if you believe in the ion trap based computers, quantum computers.
Yeah, I agree. I was around, let's say, people who work with ion traps, because I work with neutral atoms. Ions is very close. Mm-hmm. And I get the feeling as well from the experts that you cannot build a quantum computer like a small lab, or even like a big company could not do it. But if you start working on the small parts, which then will be useful for quantum computing, that's what you can really shine, because you cannot build a quantum computer. It's too much. I mean, I know that this machine looks like a room. It takes rooms. It's not.
Yes. That's exactly my point, right? And we took the similar path in the software, right? We reduced there was a textbook implementation of multi-control X or multi-control Z gate, right?
Yeah.
And we took that textbook implementation and reduced the necessary gate qubit count or the gate depth when you actually implementing this by a factor of 10. So essentially, it means 3 years of development of the quantum computers, right? Whatever you can run on the first existing quantum computer, you can run 3 years earlier using our software. So we are working on the small details, implementation of the single gates, algorithms at the very low level. That's what I think will be useful regardless of how you eventually implement this stuff, right? Those efficiencies make stuff possible earlier, and that's where the battle is at the moment.
Yeah, actually for me, because I'm coming from the hardware background, for me it's very interesting what's the main challenge for the quantum software. Like because it seems like it's quite a growing community of quantum software developers, especially startups. So what's the main challenge for them? Because I know what's the main challenge for the hardware, just make more qubit and make them more reliable. Simplifying, but what's the main challenge for the
okay, so if we want to talk about that at that level, I'm accepting what you said. So imagine then you can run the useful computation and you calculate the number of qubits and the gate depth you need for that, right? And then somebody comes and says, well, actually, you can do that with a factor of 10 less resources. And that's the software we are working on. We don't touch the application level. I think that everybody who's doing the quantum chemistry, who's doing the portfolio optimization, who is doing the especially machine learning on quantum. It is way premature. It is way premature. The same goes with the software companies who are building the SDKs, like the environment for building quantum software. Come on, there are no atoms. There are no basic operations perfected, right? And you build something which is several layers of abstractions above this. Think about how the software was developed for the computers. I'm old enough to remember the gear or PDP-11, right? Okay. You were essentially programming this thing in the assembler language, right? You were very close to the hardware, and nobody even tried and thought about building higher level abstractions. And building those higher level abstractions in the regular software came at the cost, right? Yeah. I wrote my first text editor for money in Poland many years back, right? It was 3 kilobytes, right? And had all the Polish characters, was able to communicate with the printer, and did everything which the word processor should do, right? Even adjusting text, 3 kilobytes downloaded to the machine. Try to do that with Word today, right? Or any other software. And that's the price you pay, right? For the higher level abstractions. So obviously, when the machines will show up, they will be small. They will be at the border of usability. So adding those factors, come on, it's I would think it's like 4 or 5 orders of magnitude, right? So developing this today is just waste of time.
So you don't think we need sort of assembler for quantum computing?
Well, actually, everybody does work in the assembler, but there are people who think that they can skip that and work on the very high level. Like, let's do the application development environment for quantum computers and magically get it translated to the actual hardware. Again, we did that for 2 different architectures. One is fully connected. The other one has limited connectivity. And we thought, well, we'll not be gaining much on the fully connected one. Wrong. It's just different techniques, but still you need that kind of the very low level optimization. And jumping on building the high level stuff before you perfected the low level, it's in my opinion, waste of time, because it didn't work that way when you were developing the regular computers and the regular software. It didn't start with the SDK. It started with the assembler language, right? People who could read actually the hex dump. You are too young to remember this, but we were reading hex dump. You got prepared for that by learning, and it was easier, right? You were just having a chunk of memory dumped into your screen, and you were checking for errors that way, right? It was just that way. Nobody would work that way today, but for the quantum computers you have to, because they cannot do much more, right? There's no way you can add the necessary layers in this stack to be able to work at the much higher level today. It will change, obviously, right? But it's the several orders of magnitude resources needed.
Yeah. And now if we're talking about, let's say, software community, so people who develop software for the quantum computers, like, because right now, let's say it's quite a few companies. So everybody agrees with your idea, or they still think now we should really...
I don't know whether everybody agrees, but we work with several companies globally who took their chunk and working on the real stuff, right? I shouldn't be actually the advertising other companies, especially without pay from them, but to control. They develop the pulses which go into controlling the qubits, right? And they do that more efficient than the hardware manufacturers. But it's very narrow specialization, right? Necessary. If you can go like an order of magnitude, you should be doing this, because it will be that order of magnitude more efficient. And this is still constrained. The whole development is constrained by the resources, number of qubits, gate depth.
Yeah. And do you think that we are already at the moment when we can sort of merge the software with real world problem, because now this is the whole point of the software. People developed hardware, and we want to solve with this hardware the real world problem, right? And this sort of what the software is supposed to do, because it's supposed to merge these two worlds. It's not like we developing hardware just for fun, we keep it in our labs. We want to eventually solve.
Naturally, you need the co-development, right? But what the real problem is, it begs the definition. It's far away from solving like the portfolio optimization, for example. You cannot do this efficiently on the existing hardware, right? So today the real problem is, can I have my computer to run for the circuit depth of 100? That's a real issue, right? And how do I change one of the important algorithms so it fits into what the computer can do? How big would that be, right? And that's, several of us are working in that area, a different level of stack, right, of the software stack. So low level is like the Q control, working on the pulses to control the actual qubits and implement gates. There are people who are working on the FPGA, because you need to do it fast, right? You need this control, like the fastest signal processing you can have. So there are people who are programming FPGAs for this, right? This slightly different level, and it is completely classical. And then you have people like us who are working on the gate implementations. You can actually have an approximation to any operation on the quantum system into the 1 and 2 qubit gates of the certain sets, right? And we try to translate higher level constructs into this as efficiently as possible. So that's another layer. All those can be verified on the existing hardware. You either fit and get results or not. But if you go to higher levels of this stack, out of sudden it gets difficult. You start waving your hands, right? Because some of those are heuristics only. So you cannot prove that they will scale. You cannot prove that they were operated at larger scales. And some of those are really cornerstone, like the HHL, which is a core for machine learning, and some solutions of quantum chemistry. Well, there is no proof it will be actually better than the classical one, because there are assumptions and you cannot tell. And I guess the nature is pretty malicious, in a sense that we will be most likely able to solve the hydrogen atom fast and not much more, which my students were solving with the pencil and the piece of paper like 30 years ago, right? And those hard cases will be hard, right? Meaning you need a real computer and the real methods, not heuristics. The methods which you can prove that they will scale with your problem. This is tough.
Yeah, but I agree. I agree it's absolutely tough. But let's live in ideal world for a while. How many qubits you would really like to have? I mean, with real assumptions, because you can say 1 million qubits and they're amazing, but that's probably not going to happen very soon. But how many qubits you would like to have to realize, let's say, something already decent?
All right, already decent. Breaking RSA, so you can steal money from the banks, right? We all love to do this, right? Recent results show that you don't need millions of the circuit depth. You need hundreds of thousands. And it also means hundreds of thousands of qubits. So that's where, and by the way, if I add just one digit or one bit to the RSA, you are out of luck, right? The slightly bigger prime number. And then you'll need to catch up with this, right? Luckily, this is polynomial. The Shor's algorithm scales polynomially. But again, it might be too much, right? So we are talking the useful problems, useful quantum computers, we are talking hundreds of thousands of qubits.
Yeah.
Logical ones. So then add the error correction on top, the proper error correction, and fault tolerance.
Okay, maybe I'm very positive. Let's say that I'm very positive. For me, the number 100,000 seems on the really high level, in a sense, like, Yeah, because I feel like some people already start investing in how to protect Bitcoins, how to develop a new quantum algorithm which will be quantum computer resistant, right? And I agree that cracking these primary numbers codes is hard, but 100,000, it seems like too much.
Well, it's much more efficient than classical, right? But
Yeah, okay.
it scales better.
Well, okay, sure. But do you think it's a problem of the software? We don't have a good algorithm to solve it, or just really like we just need this
No, the
qubit?
Shor's algorithm is perfect, right? It's way better than anything known classically. But it's I think the third power of the number of bits in the something like this. So yeah, we need a lot, and people who are now engaged in the pissing contest who has a bigger quantum computer, I think might be missing the point, right? I'd rather search for the company which tries to have the vertical integration, perfect the qubit, perfect interactions with qubit, perfect interaction between this qubit and other qubits, and then scale, rather than go for this unstable system which has one qubit more than the competition. It just doesn't do much, right?
And right now we have this, to say, quantum clouds from big companies which you can try to play with algorithms. I think it was IBM Quantum Challenge, something like that. You can really try to do some algorithms. There are clouds, so you can already test some algorithms. But is it really like in the baby steps, what you're saying? Because
it is baby steps. Those are small. And by the way, the last... Right, so I can tell you the story about the last IBM Quantum Challenge. The actual algorithms were tested against the simulator, not the actual computer, because they were too big, right?
Okay.
And there was the rule change or an ambiguity in the rules. But originally, the authors didn't expect the solution better than million circuit depth, right?
Okay.
So they put a limit. They didn't accept any solution below 10,000 circuit depth, because if you had, they thought that if you had anything shorter, you were cheating doing the classical computation, right? Because it was doable. And yeah, our guys shown the result under one set of rules, the most prevalent set of rules, showing the result for 4,000. We padded the result to 10,000, so it got accepted, but then we negotiated. So it got accepted as it was. But then there was slightly other implemented interpretation of the rules, which allowed for even shorter solution. One Japanese guy got into also 4,014 or something like this, right? But under this set of rules, you could reduce that to 200, and which one of our engineers have proven. So you are now, when you say 200, it's something which can be done, I guess, this year, right?
Yeah.
So you see how much it depends on the software and understanding on the... If you ask me, I think that the guy was breaking the rules, but still, division between what you do classically and what part you are doing on the quantum computer can reduce your gate count from 1 million to 200.
Yeah, but this is a lot, you know, like maybe we just...
This is a lot. That's what I'm saying. This is a lot, meaning a lot of effort should be put into that area, because we might reduce the necessary resources. Google wrote a paper doing the sort of estimations like we are just doing, right? Their claim is that the quadratic speedup guaranteed by Grover's optimality of Grover's search. You can take essentially any classical algorithm and make it quadratically faster on quantum computer. Seems like a lot, right? You are not needing 10,000, you are needing 100, whatever it is that you need, right?
Yeah.
And they have proven that it's not enough. You'll be better off the crossing between the capabilities of the current classical HPC and the benefits of getting quadratic speedup are if your runtimes are of the order of hundreds of years, right? There are no such computations now, right? So you need better algorithms, and then the exponential speedups over the classical counterparts which for me means we are in for the simulation of the quantum systems again, because we know it can be done efficiently, and not trying to build the universal quantum computers, at least for the early stages of the usability of those. Those are important problems, right? If you find the catalyst which can do the nitrogen fixation, you are good, right? And the humanity is much better off than we are today, energy-wise and cost-wise, right? So they are useful problems, but it will not be universal quantum computing and the advantage there anytime soon. It will be extremely clever algorithms, like the story which I just described, from million to 200 gates, right? By the appropriate division of labor.
Yeah, so maybe at the end, it's just a matter of creating a smart algorithm for the amount of qubits we have. So if we have just 200, maybe we just have to figure out what we can do with them.
I like the way you are thinking. We made a proposal like this. We did a lot of work on the pure mathematics, a certain graph problem. And we showed that we can actually do it in such a way that rather than needing 10,000 gates, we can have just 100 qubit and the 100 gate depth, which gives you the same 10,000 if you multiply one by the other. But it took a lot of the pretty novel math. We did publish this somewhere, pure graph problem. But yes, I think that's the direction. Find a problem, try to understand classically what gains you can get, and then try to fit the necessary part, the hard part, into existing quantum hardware. Yes, agree.
Yeah, maybe one more point which I want to touch. Let's say I'm not sure how things are going in Poland, but let's say I'm based in Netherlands, and in Netherlands, let's say most of the startups is growing from the research labs, and with decent support from the government or from institutes from the growing, and that's how they become quantum startups. Is it like a case with Beit? They grow from the research lab, or it was like assembled not from academia?
Originally, we got the research grant. Didn't grow from the research lab. I was in the business side of things for many years, but the three co-founders of Beit are coming from Google, and Google was kind of a research organization, right? And the thinking was much more valued than any other company. So that's why how we started. However, if you compare the European programs or national programs in France, in the UK, now outside of the EU, but in Germany, in Austria, we don't have anything comparable in Poland. Regretfully, we don't have anything comparable. So essentially, we created Beit in such a way that we have a holding company which is the US based. And yes, there is a lot of help there. So, and it doesn't take much effort to actually build an American company, despite having its R&D site in Krakow. That's doable, right? So we can benefit from the best of both worlds.
Yeah, and then maybe I know for creating a new hardware, you have to really invest a lot, in the sense that if you're building a quantum hardware, these machines takes room. And I know because I work with neutral atoms, I build 3 of them. So I know they really takes rooms. But what do you need to establish a startup in quantum software?
Well, actually, not much. You need extremely bright people, and that's where we were so focused on our recruiting. We are, again, I can say this as an ex Google engineering director responsible for hiring. We are much more selective than Google, right? It's harder to get to Beit. We require stuff which is harder to get than what's needed for the Google engineers. So getting good people, and then not much. As you said, you can access some of those machines remotely. You can build your software emulators, which can be bigger than the actual existing quantum computers, which we did. You can go to our website and see the emulator which solves the quadratic optimization problem exactly rather than approximately. So you don't need much, right? In a sense that you can get the credits for startups from the platform of your choice, be it Amazon, Microsoft, or Google. So you have the resources to do your simulations. And then you need bright people, and that's it, right? If you do software, that's all. But then you need to convince the hardware guys that you have something of value to offer to actually run this stuff on the real machines. Without this, I don't think we'll be offering any value, right? So for example, we have run our core key algorithm on the existing hardware, both superconducting and ion trap. And then we have formally, mathematically proven how the scaling would look like, right? So we know that you can use that regardless of the size of the quantum computer. 2 steps of the induction proof, right? Do it for n equal whatever the n is, and then show that from this, it follows that you can do that forever, right? So you need to establish partnerships, and for that, you better walk the walk rather than talking the talk and wave your hands, right? Have solid results and it will come.
Yeah, and so I think maybe for the small companies, is a mistake in hiring, it costs you more because your team is small.
Of course.
Yeah.
Of course.
Because I'm working in a lab, and let's say usually in the machine you have 3-4 people, and if you're hiring a few people who cannot really help you, then you're stuck with, it's really 4 people, so it's 25% of people.
That's one thing, but it's even worse if you consider growth. And there was this old saying, and I hear that repeated: A-class players attract A-class players, right? Because we want to solve harder problems, and you need all help you can get. So we were essentially hiring people better than us. I know that many people are saying this, but we actually do this. I know I cannot do stuff which my young hires can do, right? And B-class players attract C-class players, so they are not the worst ones, right? So you can, in the growing company, you cannot afford bad hire. You are just dead on if you do this, right? Because it will mean that there will be worse and worse people joining your company, and the chances that you will be doing breakthrough research just don't exist anymore.
Yeah. Well, I think it was very nice talking to you. You had very interesting ideas and opinions, which I think a bit controversial and maybe shake some thoughts in some heads, but I think they're definitely very interesting. So it was very interesting.
I'll tell you something, and I don't know how official it is, but I don't care much. I'm old, so old men have no shame. When we started at CDL, the accelerator, everybody told us to pitch the actual solutions because they were investors who knew how to grow the companies which were just entering the market, right? So we were told to pitch the actual solutions to the real world problems. And physicists in me couldn't agree, right? We don't have software, we don't have hardware which can attack the real world problems. And they were really pissed off at me, right? Now there is another quantum cohort in that accelerator, and those guys are told not to mention quantum for the next 5 years. Just focus on the classical part. Well, it took just 2 years to come to the conclusion, which we were, there is still scientists in me. In a sense, I want to be honest, right? I would not say stuff which I cannot prove. Not only believe, right? Science is not the place for beliefs, right?
Yeah.
I can have ideas, and then I go and verify them. And if they fail, I learned something, right? If they succeed, I learned something. It's not that's how it works at this cutting edge of the technology. If you start cheating, you are doomed, right? It will get exposed sooner or later. And then what happens to your company, the technology and stuff? So yeah, what you hear is something which I can stand for.
Yes, no, I think and especially it's important if you want to invest in something. When you put your own money, let's say, you invest for somebody, then you really want to hear harsh truths right now, then you will regret in 5 years.
Yeah, exactly this.
That's true. Okay, thank you very much for joining me. It was a pleasure.